Alrighty, we are going to continue on with our probability unit by diving into independence and mutually exclusive events. All right. So we're going to be going to compound probabilities, basically, like multiple events happening in a row. Say you roll, one die and then another one, right? That's two two events happening in a row, both with their own probability. All right, so we are going to be jumping into that. Fantastic. So an example here. If you, the probability of a single flip of a coin, like getting head on a single flip of a coin, is 1 out of 2. If you flip the coin and get heads a second one, right, it's still 1 out of 2 the second time. So I flip a coin, probability of me getting heads is 1 out of 2. What's the probability of me getting heads on the second flip? Well, still 1 out of 2, right? So did the first event affect the second? Or did the second affect the first? No. All right? So these ones are independent events. They are independent of each other. One does not affect the other. So we can jot down what independence is. It's when the first action does not affect the second probability, or vice versa, right? So they're not affecting each other. That's known as an independent event, or independent events. All right. So let's say they're not independent events, right? If you have a jar of cookies with 7 chocolate chip cookies and 3 peanut butter cookies, and say the probability of getting a chocolate chip is then, right, 7 out of 10. Okay. So I've got a 7 in 10 chance of getting a chocolate chip. Say I eat that chocolate chip, right? Now, is my probability for the peanut butter still 3 out of 10? Well, no. Now I only have 9 cookies because I ate that. I'm not going to put it back. Who would do that, right? Now I'm 3 out of 9 for a peanut butter. So this was chocolate chip right here, probability of getting a chocolate chip. Now this is probability of a peanut butter, which would, I guess, it would then simplify down to 1/3. But the taking out and eating of that first cookie changed my probability of the second one. Therefore, these are not independent events. The first one happening affects the second one. So just another way of writing this definition, we already wrote something down like this, but two events, A and B, are independent if the fact that A occurs does not affect the probability of B occurring. Or vice versa, right? It can go the other way as well. B does not affect A does not affect B. Independent. Woo! Awesome. All right, so some more examples here. So tossing a coin and getting heads, and then selecting a purple marble from a bag. Those two are independent. Right? Flipping the coin's not going to affect those marbles in the bag. Cool. Getting heads after tossing a coin and rolling a 2 on a single 20-sided die. Again, these are independent. One does not affect the other. The coin's not going to affect the die. Choosing a jack from a deck of cards, replacing it, and then choosing a king as a second card. Well, is choosing the jack that you then replace going to affect getting a king on the second card? No. And what's the key word there? What's the key thing happening? Replacing. Say I chose a jack, right? I have a 4 in 52 chance to get a jack, right? Probability of drawing a jack. Which would then simplify down to 1 in 13. Well, say I don't put it back. What's the chance of drawing out a king now? Well, the probability of drawing a king after that has happened, right? After it, and I didn't put it back, that's now 4 out of 51. So that completely changes it if I remove it, right? This is a separate example. If I don't put it back, that is the key thing here. I did not replace. No replace. So my probability changes the second time around because I didn't put it back, right? That's not what this example is saying above. This is like a little side one, like an extra little problem here to have you guys see both sides of this, all right? So if you replace it, independent. Don't replace it, obviously it's going to affect the second one, not independent. All right, so now we are going to look at the probability. What's the probability of rolling a 6 and then getting heads on a coin flip? Okay. So we can use like a list, a tree, a Venn diagram. Oh my goodness, all sorts of fun stuff. All right, well, let's see here. I'm gonna go with the tree. I guess that'll be my choice here. Probability of rolling a 6, and then getting heads on a coin flip. So my possibilities for my die rolls are 1, 2, 3, 4, 5, and 6. Obviously, the winner is 6, right? Then I'm gonna flip that coin. Oop, that's not what I wanted. So I get heads or tails. Heads or tails. So on, so forth. And I'm going to pop over here to the 6. Heads, tails. So I could roll a 1, then flip heads. Roll a 1, then flip tails. Roll a 2, flip heads. Roll a 2, flip tails. So on and so forth. So how many possibilities do I have? Well, this goes back to our fundamental counting principle. If it's 6 events, then 2 events, that gives me 12 total outcomes. So I'm going to write my probability up here with my denominator being 12. Okay. Well, how many successful outcomes do we get? I want to get 6 and then heads on the coin flip. Well, that is only happening here. 1 out of those 12. Okay? 1 in 12 probability of this actually happening. And there's a nice little way to do this. If they are independent events, right? One doesn't affect the other here. I've got a 1 in 6 chance and then a 1 in 2 chance. If I were to multiply those together, I get 1 in 12. That's awesome. Cool. So here we go. This is exactly what I was just talking about. To find the probability of 2 independent events that occur in sequence, find the probability of each event occurring separately, then multiply the probabilities. This multiplication rule is defined symbolically below. Note, multiplication is represented by and. Okay? I take my probability of the first event, which was 1 in 6. Probability of the second event, which was 1 in 2. And boom, I got my 1 in 12. Cool. All right, so what is the probability of rolling a 6 and then rolling a 5? Well, it's 1 in 6. Then rolling a 5, well, it's still 1 in 6. So I've got a 1 in 36 chance to make this happen. Rolling a 6 and then rolling a 5. All right? 1 in 36 chance for any of those combos of dice. All right, given a bag of marbles with 3 red, 2 green, and 5 yellow, what is the probability of choosing a red, replacing it, then choosing a green? Well, let's see here. I've got 3 plus 2 is 5 plus 5 is yellow. So I've got 10 possible outcomes, or 10 possible marbles to choose from here. Right? What's the probability of choosing a red? That's 3 out of 10. Then replacing it, then choosing a green. Well, the green is 2 out of 10. So if I multiply these bad boys together, I'm going to get 6 over 100, which can simplify down to 3 over 50. That's pretty dope. All right, so now we get into mutually exclusive sets. All right, so mutually exclusive and independence are 2 different things, which can be confused at times. So mutually exclusive, that means that they don't share any elements. Okay, independent sets are those that don't impact each other's probabilities. So those are 2 totally different things. All right, so mutually exclusive is about the sharing of elements. It doesn't share any of the elements, then they are mutually exclusive, and we'll get into some examples. So, in the example to the right, and it's kind of just floating around there because that's how it was imported, these events are not mutually exclusive because there's an intersection between the 2 sets. So there's a chance that both event A and B can happen, right? There's a chance that both of them can occur. So they are not mutually exclusive, all right? But you can check and see if the events are independent of each other. The way you check that is, well, I know the probability of A and B happening is 0.15. per the Venn diagram. Now I can also check and see if, mathematically speaking, with my fancy little formula type dealio that I got, if I took the probability of event A happening, and the probability of A is 0.3. Why is it 0.3? Well, 0.3 because 0.15 and 0.15 added together gives you 0.3. And then I can take probability of event B for the same reason. I would have 0.35 and 0.15. Add those together, I get 0.5. If I multiply those two, I get 0.15. The exact same thing that's in the intersection of those two in the Venn diagram. Therefore, since these two are the same, they are independent events. So I can ask you a question, are these events independent? And you have to figure that out based on those Venn diagrams. All right. So not mutually exclusive. They are independent. Two totally different things. Do not confuse them. So you've seen replacement and no replacement here already, or at least replacement for the most part. But they use a lot around probabilities because they can change what your probabilities are later on if there's multiple events happening, right? So replacement and no replacement are used all the time in compound probabilities. So did you put it back? That's replacement. Did you keep it? That's no replacement. So let's see that in action here. Getting a green marble, replacing it, and getting a green marble. Or picking a black queen, not replacing it, and getting an ace. Well, those are, when you're replacing it, I'm putting it back into this little bag of marbles or whatever, right? So I've still got the same numbers once I've replaced it. But if I pick out a black queen, right, a spade or a club, queen, and I don't put it back, now I go from having 52 cards to 51 cards. I've changed it. So these are non-independent events because getting that ace, the probability originally was a 4 out of 52, but now it's a 4 out of 51. So things change. All right? Replacing gives you independence. Not replacing, not independent. Woo! So as we have here that I just said on the last page, replacement tells us that the events are indeed independent. I would jot that down if you didn't already. And we have no replacement tells us that the events are not independent. All right? If I don't replace it, it affects the probabilities. The probabilities are altered. Once again, I would jot that down if you have not already. Like a college professor. Now write that down. And in a formal way of writing it down, testing for independence, which we did a few problems ago. If you're looking at a Venn diagram, or I tell you that the probability of A and B happening is one thing, and you know the two independent or the two individual probabilities, you can test for independence. If the probabilities, and this is on a different line, so I'm just going to rewrite it again. A and B happening equals the probability of the event A happening times the probability of event B happening. If those are equal, you have independence. If they're not, you don't. It's as simple as that. All right? Again, I'd write that down. So let's take a look at this example up top here, and I believe this is supposed to be, animated and have the answer fly in, but it doesn't do that when it converts to PDF. Sorry. All right, the probability of A is 0.8, and the probability of B is 0.4, and then we also give you the probability of A and B occurring, which is 0.2. Well, 0.4 and 0.8 multiplied together, so 0.8 times 0.4, well, that equals 0.32. That's not 0.2. So since they're not equal, it's not independent. Okie doke. These are not independent events because the probability of A times the probability of B does not equal the probability of A and B. So if we look at this example, well, probability of A is 0.6 and probability of B is 0.5, and A and B is 0.3. Therefore, well, if I take these two, 0.6 and 0.5, that equals 0.3 when I multiply them together, which is the same as the probability of A and B. Therefore, they are indeed independent in this case. All right? So that's how we would check for independence. A great question for a test. Are these two events independent? Or if they're independent, what's this probability? So you could potentially have to backtrack, figure out a different probability, right? I could say A and B are independent events. The probability of A is 0.6. Whoops. Probability of A is 0.6. A and B is 0.3. If those events are indeed independent, what's the probability of B? And you could solve a little equation to get 0.5. Okay? Woo! All right, so in this problem here, we got a Venn diagram. We want to figure out our different probabilities of A, B, A, and B. We want to see if they are independent. All right? So set probability of set A, right? Probability of it being A would be, well, I got to add the 0.25 and the 0.25, and that would give me 0.5. Excellent. So I got to make sure I include that overlap. Set B, well, same idea. It is going to be, once again, 0.5 because I'm adding 0.25 and 0.25. The probability of A and B, well, it's already written there for me. It is 0.25. All right. Now let's see if they are independent events. So to do that, I'm going to multiply the probability of A times the probability of B. So 0.5 times 0.5, which is, drum roll please, drum roll, 0.25. Okay, so I get 0.25, which is the same as probability of A and B per the Venn diagram, thus independent. Excellent. America, freedom, rock and roll, Costco. Yes. Cool.